You know, when you sit down in a massive theater to watch a Broadway show, there is this natural expectation to just like focus entirely on the actors.
Oh, absolutely.
Right. The spotlight hits the stage,
Yeah.
the lead sings their big solo, and your attention just stays locked right there on the performance.
I mean, it's just human nature. We naturally focus on the part of the machine that is, designed to be seen.
Yeah, exactly.
Yeah.
But if you were to actually look up into the rafters or peek behind those heavy velvet curtains, you'd see a totally different reality.
Oh, for sure.
You'd find this incredibly complex hidden world of pulleys and tension rigging and stagehands moving these multi-ton set pieces in total darkness.
Yeah.
The show doesn't actually happen because of the lead actor. It happens because of the invisible infrastructure just running silently in the background.
Which is honestly a remarkably accurate lens for looking at the global shift toward electric vehicles. Because we are constantly staring at the lead actors, the sleek, new personal EVs parked in neighborhood driveways, or those futuristic dashboard screens, or the crazy 0 to 60 time.
Oh yeah, the shiny stuff.
Exactly. But the real structural revolution isn't actually happening in your driveway.
And that hidden infrastructure is exactly what we are pulling apart today. So welcome to this deep dive.
It's a great topic.
It really is. We have this fascinating stack of sources that prove the most aggressive leaps in the global EV transition are happening entirely behind the scenes.
Yeah, completely out of view for most people.
Right. So today we are looking at a deep market report from Krapler detailing a sudden massive shift in China's fuel demand, plus the newly released 2025 Utah Electrification Initiative annual report.
And some really cool breaking industry hardware and software developments out of Australia and India.
Yeah. And when you synthesize these developments for a deep dive like this, you realize that the narrative of consumer preference, like, people wanting a quieter commute or a greener car, is barely a footnote.
It's so true. I mean, a true driving forces are heavy commercial freight, mobile rescue technologies, and the really intricate negotiation of neighborhood power grids.
So to really grasp the scale of this, we have to start with the biggest energy guzzlers on the road.
The heavy-duty trucks.
Exactly. According to the Kepler market report, China's demand for gas, oil, and diesel is set to definitively peak this year in 2026.
And I just want to emphasize, from a global energy market perspective, a permanent peak in Chinese diesel demand is a massive watershed moment.
It's huge.
Kepler is projecting an expected annual decline of 2.7% from this year all the way through 2040.
I want to look at the mechanics of why that decline is happening so rapidly. Because it kind of goes against the traditional assumption that heavy industry is the hardest sector to change.
Right. People always say freight will be the last to go electric.
Yeah. But get this, heavy-duty vehicles, those massive commercial transport trucks, make up only 10% of China's entire vehicle fleet.
Okay.
Yet, they consume nearly 40% of the total road fuel in the country. It's like the Pareto principle on steroids, like an extreme 80-20 rule, the 10-40 rule, basically.
Well, because a heavy-duty truck just isn't used like a passenger car. I mean, your personal vehicle probably sits parked for, 22 hours a day?
Yeah, at least. Just sitting in the driveway.
Right. But a commercial truck is a specialized asset designed to be in near constant motion. It's hauling maximum tonnage.
So the energy required to move that mass continuously is just staggering.
Exactly. And that is why diesel has maintained its monopoly for so long. It is just incredibly energy dense.
But the Kepler data shows that monopoly breaking, like right now, in the first half of the year alone, sales of liquefied natural gas or LNG trucks in China jumped by 104%.
Which is a phenomenal spike. And it's driven entirely by raw math.
Really? Not government mandates?
Well, there are subsidies. You have highly attractive pricing for alternative fuels, coupled with aggressive government scrap subsidies. They're offering up to $11,000 for retiring old, inefficient diesel vehicles.
Oh, wow. So they're literally paying them to ditch the diesel.
Yeah. Fleet operators aren't making this switch for environmental optics. They are doing it because the operating cost per mile has tipped fundamentally in favor of LNG and new energy electric trucks.
And the volume of diesel being pushed out is massive. I mean, these new trucks coming online are projected to displace roughly 110 to 135,000 barrels a day of diesel demand just this year.
It's wild to think about.
It really is. That tells me that tackling this specific 10% of heavy trucks is the actual cheat code to decarbonizing transport.
Oh, absolutely.
Like when the heavy logistics industry pivots based on pure economics, the entire global energy market permanently shifts.
And that global shift creates an immediate severe challenge for local infrastructure everywhere else.
How so?
Well, if massive heavy transport fleets are adopting alternative fuels and electricity at the scale China is demonstrating, it forces power grids in places like the United States to brace for a tsunami of new energy demand.
Which brings us perfectly to the 2025 Utah Electrification Initiative Annual Report. Because Utah is right in the crosshairs of this logistics shift. They have something like 10,000 heavy commercial trucks moving through the state every single day.
Yeah, and the report highlights a really crucial technological divide in handling those trucks.
The difference between short haul and long haul, right?
Exactly. Short haul, freight-like local delivery routes, port to warehouse transfers is highly electrifiable right now with current battery technology.
Because they just go back to a depot to charge overnight.
Right, the vehicles return to a depot every night. But long-haul freight passing through the state requires a technological leap that standard infrastructure simply cannot support.
I mean, it makes sense. You can't have a commercial semi-truck carrying perishable goods across the country, pulling over to sit at a charging station for 6 hours.
No, it destroys the entire logistical model.
To solve this, Utah's Espire Center is building something at their inland port that honestly feels like it belongs in a sci-fi novel, but it's very real.
The wireless charger.
Yeah, a 1-megawatt wireless charger.
The engineering required to pull that off is just staggering. I mean, a standard level 2 home charger might draw 7 to 10 kilowatts.
Okay.
And a fast public charger for a passenger car might push, say, 150 to 350 kilowatts.
Right, the ones you see at grocery stores.
Yeah. But here, we are talking about 1,000 kilowatts.
Wait, how does that actually work without melting the pavement? You can't just push a megawatt of electricity through the open air like a Wi-Fi signal, can you?
No, definitely not. It relies on magnetic resonance and inductive coupling.
Okay, what does that mean in plain English?
Essentially, you have a massive primary copper coil buried in the ground pad and a secondary receiver coil mounted to the underbelly of the truck.
Got it.
When alternating current flows through the ground coil, it generates a highly oscillating magnetic field. The truck's receiver coil tunes to that exact resonant frequency, capturing the magnetic energy and converting it back into electrical current to feed the battery.
Oh, wow. So the energy transfers as a magnetic field, not as raw electricity sparking through the air.
Correct. It's safe, but moving a megawatt of power that way generates an immense amount of thermal load.
I bet. It must get incredibly hot.
It does. The system requires incredibly sophisticated active liquid cooling lines running through the charging pads, and the physical alignment of the truck over the pad has to be really precise to maximize efficiency and minimize wasted heat.
So they are pairing this technology with a Class 8 Kenworth battery electric semi-truck. The idea is that the truck parks over this megawatt pad while it's being loaded or unloaded, right?
Yeah, and it can charge in just 30 minutes.
That's crazy fast for a vehicle that big.
It is. That half-hour burst gives it enough energy to run a 400-mile daily UPS delivery route.
But stepping back for a second, if a single commercial truck is suddenly pulling a megawatt of power off the local grid in a 30-minute window, and you scale that up to thousands of trucks.
Yeah, you introduce a catastrophic strain on regional power stability.
That is basically the power apocalypse scenario. If you're just a local resident paying a utility bill, unmanaged charging at that scale is your worst nightmare.
Oh, for sure.
It means transformers blowing out, rolling blackouts, and ultimately the utility company passing the multi-billion-dollar cost of building new power plants directly to your monthly bill.
And the data from Utah proves that load is accelerating fast. EV adoption in the state jumped 36% just between 2023 and 2024.
Wow, 36% in 1 year.
Yeah. They now have over 65,000 light-duty EVs on the road, alongside this incoming wave of heavy commercial freight. The grid simply wasn't designed to handle tens of thousands of massive, simultaneous power draws every evening.
But the Utah Electrification Initiative has a defense mechanism built into their strategy, which they call Smart Energy Management, or SCM.
Which is such a brilliant approach.
It functions essentially as air traffic control for electricity. Instead of spending billions to build a massive new airport to handle more planes, you just use software to perfectly time when every single plane lands.
Air traffic control is a great way to visualize it. But instead of routing physical planes, the software is routing voltage and adjusting to microsecond fluctuations in the local neighborhood power supply.
Because without it, everyone just charges at once.
Exactly. Unmanaged charging assumes that when a vehicle plugs in, it immediately pulls maximum power until the battery is full. But smart energy management intercepts that demand.
How so?
It reads the real-time load on the grid, looks at the wholesale price of electricity at that exact second, and dynamically adjusts the power flow to the vehicle.
I want to push back on the reality of that, though.
Sure.
If SCM is actively delaying or throttling power to protect the grid, what happens to the human being at the other end of the plug?
That's the big concern people have.
Right. Say I get home at 6 p.m., my battery's at 5%, and I plug in. But at 8 p.m., I have a sudden family emergency, and I need to drive to the hospital.
Yeah.
Am I just trapped in my driveway because the grid software decided it was cheaper to wait until midnight to charge my car?
It's a totally valid question, and it's where the engineering of the system is actually quite elegant.
Yep.
SCM isn't a hard lockdown. It operates on user-defined parameters and microtransactions. When you plug in, the protocol communicates your baseline requirements.
Like a minimum charge level.
Exactly. For instance, you can set an override that ensures the car must immediately reach a 20% state of charge, regardless of grid conditions, for exactly the kind of emergency you just described.
Oh, that makes sense.
Beyond that minimum threshold, the software negotiates. The utility company is essentially offering you a financial incentive, like a microcredit on your bill, to allow them to throttle your charging speed during peak hours.
But I'm still in control.
Yeah, you retain the ability to override it through an app if you are willing to pay the premium peak pricing.
So it's like an invisible real-time auction happening between my car's onboard computer and the local utility transformer.
Precisely. And the macroeconomic impact of that software negotiation is staggering. By smoothing out those demand peaks, Utah projects that through intelligent coordination, they can avoid having to build 6 gigawatts of grid upgrades by 2055.
Let's break that number down for a second, because a gigawatt is massive. They were avoiding 3 gigawatts of new power generation and 3 gigawatts of transmission and distribution infrastructure.
Just to put that in perspective, building 3 gigawatts of new generation isn't just like stringing up a few more wires on a pole.
No, definitely not.
It means permitting, funding, and constructing multiple large-scale power plants from scratch. It means laying high-voltage transmission lines across hundreds of miles of private and public land.
Right.
The capital expenditure for that physical infrastructure is astronomical.
And by avoiding those bills entirely through software management, Utah projects a savings of more than $10 billion.
It's incredible.
$10 billion saved simply by having the grid tell chargers how to stagger their power draw.
And they are maximizing this efficiency at centralized locations they call multimodal hubs.
What exactly is a multimodal hub?
These are nodes where heavy public transit intersects with the grid. Utah currently operates 73 electric public transit buses. Rather than treating those buses as isolated energy sinks, they integrate their charging schedules with commuter train systems.
Oh, so everything is talking to everything else.
Yeah. Stather Rail is actually expanding its Salt Lake City headquarters right now to include a novel electric train battery charging station.
So the heavy freight trucks pulling megawatts, the city buses, the commuter trains, and the thousands of passenger cars and residential garages are all basically sipping from the same intelligently managed energy pool.
And because of that coordination, EVs transition from being a liability to an active asset. Utah projects that managed EVs will actually generate $1 to $2 billion in revenue by 2055.
Wait, revenue?
Yeah. That grid efficiency lowers the base cost of electricity generation, which fundamentally reduces the utility bill for everyone in the state, even the residents who don't own an electric vehicle.
Okay, so we've established that the grid can technically survive the massive load of commercial freight and millions of new cars. The heavy engineering is totally viable.
Right.
But, infrastructure is completely useless if human beings hate interacting with it.
That is the truth.
Because the everyday driver isn't thinking about megawatt loads or dynamic grid balancing. They're thinking about the anxiety of road trips. They're dealing with fragmented, unreliable charging networks.
Yeah, the transition from early adopters to the mass market relies entirely on overcoming those psychological and software barriers. You are pointing to two very specific phenomena: app fatigue and range anxiety.
Exactly. And the sources we have from India and Australia illustrate how the industry is finally addressing these human hurdles.
Let's look at India's software approach first.
Yeah, because the EV infrastructure there was suffering from extreme fragmentation. You pull up to a charger, you have to download a proprietary app, create an account, load a $20 minimum balance, and just pray the software handshake actually works.
It creates a tremendous amount of user friction. I mean, nobody wants to do that in the rain.
No, it's the worst.
To combat this, two major Indian infrastructure players, Bolt Earth, which already has over 100,000 chargers deployed, and Charge Zone, partnered up to create a fully interoperable EV network.
Which is great, but interoperability sounds great in a press release. From a software perspective, it is a back-end nightmare.
Oh, absolutely.
You are trying to get different proprietary billing APIs, varied hardware protocols, and independent network polling systems to unify so that a driver can use over 1,500 fast-charging locations across the country on a single app.
Right.
How are they actually achieving that without the system constantly crashing?
Well, it requires adopting an open charge point protocol, basically a universal language that sits between the physical charger and the central management system.
So everyone agrees to speak the same language.
Exactly. Instead of the charger only speaking directly to the Charge Zone server, it uses a standardized API that authenticates the user's secure token from the Bolt.earth app.
I see.
The backend handles all the microtransaction clearing and real-time polling to confirm whether a charger is physically occupied or broken before the driver even routes to it. The complexity is massive, but it is entirely hidden from the user.
It cures app fatigue. The driver just sees a reliable, real-time map where they can plug in and pay effortlessly.
Yeah, it's a huge step forward.
But software can't fix human error. People misjudge distances, or they simply forget to charge.
It happens to the best of us.
It really does. And that brings us to the hardware solution out of Australia. A Melbourne-based company called Alpine Energy has essentially built the electric equivalent of a jerry can to solve the stranded driver problem.
I love this concept.
They debuted a platform called the MGEN M40.
Which is the world's first vehicle-to-vehicle, DC-to-DC fast-charging platform built specifically for mobile rescue.
This is just fascinating to me. If you run out of gas on the highway, someone can just walk up with a plastic jug and pour a gallon into your tank. But you can't carry a bucket of electricity.
No, you definitely cannot.
Instead, a rescue truck equipped with the MGEN M40 drives up, runs a thick cable directly from their vehicle into your stranded EV, and rapid charges your battery right there on the shoulder of the road.
And the mechanism of how it transfers that power is what makes it so revolutionary. It uses a DC-to-DC connection.
Why is that important?
Well, if you were to plug a stranded car into a standard alternating current, or AC, mobile generator, the power has to flow through the EV's onboard inverter to be converted into direct current for the battery.
Because batteries store DC power.
Exactly. But that onboard inverter is a bottleneck. It heavily limits how fast the energy can flow into the car.
So by using DC to DC, the rescue truck completely bypasses the stranded car's internal hardware.
Exactly. The MGEN M40 communicates directly with the stranded vehicle's battery management system. It negotiates the voltage and manages the thermal load directly, allowing it to safely dump up to 40 kilowatts of DC output straight into the cells.
Which means it can push about 65 kilometers of range into a dead car in just 15 minutes.
Yeah.
That is plenty of juice to get you to the nearest interoperable charging station.
And more importantly, it provides the essential psychological safety net that mass adoption requires.
Right, curing range anxiety.
Early EV drivers had to be meticulous planners, mapping out every single charging stop. But the general public expects transportation to accommodate human error.
We want to be able to just drive and not think about it.
Exactly. The MGEN M40 is designed for that reality, for roadside recovery, emergency response, and remote operations in places like the Australian outback, where a permanent electrical infrastructure is just years away from being built.
It perfectly bridges the gap between the pristine mathematical models of a smart grid and the messy, unpredictable reality of human life.
It really does.
When you look at all these pieces together, a deeply interconnected global engineering puzzle emerges. We've gone from the raw economic scale of Chinese heavy freight stripping diesel demand to Utah's multi-billion-dollar smart grid balancing megawatts in real time.
Yeah.
And we've seen Indian software architecture unbreaking the charging experience, and Australian engineers figuring out how to rapidly transfer power between vehicles on a dirt road.
Because none of these developments exist in isolation. The software requires the hardware, the heavy freight requires the smart grid, and the grid requires the sophisticated load balancing of millions of interconnected batteries.
And the reason you, as a driver or a homeowner, should care about this complex web of hidden technology is that its singular goal is to make the electric transition invisible to you.
Yes.
The goal is a reality where you plug your vehicle in and the system just works.
Yeah.
The power is there, it's reliable, and because the grid is actively managing the load behind the curtain, it remains affordable.
The ultimate success of the transition depends entirely on this hidden infrastructure performing flawlessly under immense pressure.
But there is one final, incredibly provocative concept that emerges when you combine these disparate technologies. Something I really want you to mull over.
Oh, this is the best part.
If an Australian truck can deploy a high-voltage battery to direct charge a stranded car, and if Utah's smart energy management software can coordinate tens of thousands of vehicles simultaneously to balance a power grid,
Yeah.
what happens during a massive natural disaster?
You are looking at the evolution of vehicle-to-grid technology.
Exactly. Think about a scenario where a hurricane or a severe winter storm takes out the traditional high-voltage transmission lines. The central power plants are cut off. Historically, cities go dark.
Right, complete blackout.
But in this near-future reality, every parked, fully charged electric vehicle in your neighborhood represents a massive reserve of stored energy.
And a standard EV battery holds enough kilowatt hours to power an average home for several days.
Right. So by combining that bidirectional vehicle-to-vehicle hardware with the macro intelligence of a smart grid, your neighborhood could isolate itself into a decentralized microgrid.
That's incredible to think about.
Your car ceases to be just a method of transportation. It becomes a mobile power plant pushing electricity back into your house, stabilizing the local grid, and keeping critical infrastructure like nearby hospitals online while the utility companies repair the main lines.
It forces us to completely redefine what a vehicle actually is. It transforms a depreciating transportation asset into a vital node of community energy resilience.
Which changes everything. So the next time you see a quiet, sleek, new electric car glide down your street, don't just stare at the lead actor. Think about the invisible megawatt coils buried in the concrete, the smart grid software negotiating voltage in microseconds, and the mobile rescue nodes preparing to deploy.
The real show is behind the scenes.
Exactly. That hidden infrastructure isn't just changing how we drive to work. It is actively, quietly rewiring the physical limits of our world.